We're now ready for lesson 1.6, and you can see our title is Solving Systems of Equations. And if you're wondering, well, what is a system of equations? I gave you a definition there at the bottom. We have two or more equations. Now for us, in this lesson, it's going to be two. When we get later in chapter 1, we'll throw another equation and another variable. We'll be dealing with three variable systems. But for today, two variables, two equations, and the solution is going to be an ordered pair, an x and a y, that satisfies, in our case, both of the equations. So to be a true solution, our numbers that we get for x and y have to make both of our equations true when they are substituted in. So let me give you an example of what a system looks like. Here is a system of two equations. And in this lesson, we're going to learn, or probably refresh your memory, on how to solve these systems, and we're going to be using three different methods. And so that's the bulk of today's lesson. So the first method that we're going to use is the graphing method. And so I'm going to show you two different possibilities for graphing. And it's not that I'm going to require that you do both. I'm just trying to help you out. Sometimes one of these methods works out better than the other. And it just depends on the system that you're given, the equations that you're asked to graph. So I'm going to do this red line in what we call, I'm going to use the graphing by intercepts method. Change my color so we can keep our two lines straight. So the red line, let me just rewrite the equation over here. So graphing by intercepts means that I can find an x-intercept. That's just another way of saying where does this line cross the x-axis. And I can find that number by substituting 0 in for y. If you plug 0 in for y, you're left with this equation. And we know that this line, when graphed, has to cross the x-axis at -12. If I left the units on the graph paper as they are, that would be way over here to the left. And now I'm going to do the same thing and find the y-intercept. Well, this time, to find the y-intercept, I'm going to let x be 0, and I'm going to solve for y. So if you let x be 0, you're just solving the equation 8y equals 36. Y is going to be 36 over 8, and we can reduce that dividing by 4. That's 9 over 2, which is another way of saying 4.5. Okay, so we're going to set those numbers aside, and eventually we're going to plot those 2 points and connect them with a straight edge, and that will represent the top line in our system. Now I'm going to work on the bottom line in the system, and this time I'm just going to use traditional putting it in slope-intercept form. So again, I'm not telling you that you have to follow this exact process, graphing by intercepts with one and then slope-intercept on the other. I'm just reviewing two different possibilities. You pick the one that you like to use the most. All right, so this has a y-intercept of -21, that's the b, and it has a slope of -6. So right away, knowing where these intercepts are, that gives me an idea of what I might have to do to give the scale, or I use the word the units, on the graph. Obviously, if I left the graph paper as it is in units of 1, I'm not going to be able to plot -21. That would be way down here at the bottom. So what I'm going to do to make all of my intercepts fit is I'm going to change my graph so that it's in units of 3. And this is going to happen from time to time throughout the year, and I don't really mind what you change the units into as long as you identify it like I've done here on your graph paper. So now that I know that each one of these lines on the graph paper is really a 3, 3, 6, 9, 12, and so forth, now let's see if we can plot our intercepts. So -12 x-intercept means I'm going to go left 4. So there's x is -12. And a y-intercept of 4.5, well, here's 3. And then I'm going to go up where I think 4.5 would be. And now you would just grab your straight edge. I'm going to pull out my line draw tool. And I'm just going to do my best to line up those 2 points. And for you, that's no problem. You can just take your ruler, and there's the line, the equation for the first equation in our system. All right, now let's work on the bottom equation of the system. So it has a y-intercept of -21. So that's, in our scale, that's like going down 7. And if I counted out a slope of -6, that would be up 6 and then left 1, up 6, left 1 again. Okay, you could do that. You can also do some inputs, outputs. If you don't like this, you could do the old input a number for x. For example, if I input -1 in for x, I get 6 minus 21, which is -15. And that's what I have here, -1, and then 3, 6, 9, 12, 15. There's that point. So you could do it either way. You can count out the slope, or you could do some inputs, outputs, and come up with points that way. All right, so let me see if I can line those points up. And the goal here when you're solving by graphing is you want to see if the lines cross. And if they cross, then that represents the solution to our system. Well, obviously this line, these 2 lines do cross. We have a definite solution. We just don't know for sure, based on where these 2 lines cross, where that point of intersection is. We know there is one, and so I chose this problem on purpose because sometimes the graphing method falls a little bit short in giving us a true picture of where the solution is. Now, that's not always true. Sometimes I will draw 2 lines and they cross at a definite point, no doubt about it. They meet at a grid mark on the graph paper that tells me exactly what x is and exactly what y is. But this is not one of those cases. So I'm going to use algebraic methods to actually come up with the exact solution. So when you run into this case, maybe where 2 lines cross, like right in a square like that, and you just don't know. You can't guess. Okay, you can't say, well, I think that's, -4.5 or whatever the number is. It looks like it's, -7 2/3. You don't ever want to guess. You want to know for sure. So that leads us to algebraic methods. Okay, so here's one of the algebraic methods that I want you to be good at. It's called substitution. And substitution says this: pick a variable in your system and solve for it. So there are 4 choices because there's 2 x's and 2 y's. So I do have 4 options, but of these 4 there is a best option. If possible, you always want to solve for the variable that has a coefficient of 1. That makes the math easy. You can do it in one step. You don't have to worry about dividing by anything. You won't have to deal with fractions in this case. So I've done solve for a variable. Now, part 2 of substitution is replace that variable in the other equation. Don't make the mistake that some people make and go ahead and turn it back in, replace it in the same equation. All right, so what I'm going to do here is I'm going to take -6x minus 21, and since I solved for y on the bottom, I'm going to replace the y on the top. And it's going to look like this: -3x plus 8, and now I'm going to replace y with -6x minus 21. And so you can see that we're going to be solving for y. I'm sorry, for x. We're going to be solving for x. All right, so distribute 8. Combine like terms. And if you need a calculator, you're going to be adding 168 to both sides. It's 204. Divide by negative 51. And we got our answer for x, which is negative 4. Now the answers will be ordered pairs if you have just one answer. So we know x is going to be negative 4. And now to find y, you have choices. You can take this value for x and replace in really any of these. I think it makes sense to go ahead and use this one because it's already set up to find out what y is if you plug in x. So if we let x be negative 4, we get 24 minus 21, and we get a y value of 3. Okay, now let's go back to our graph and see if that's reasonable, that these two lines cross each other at the point negative 4, 3. Yeah, I would say definitely, because this is negative 3. Now, maybe because, you know, I'm guesstimating where these points are. Maybe you're thinking, well, that doesn't look like negative 4 to me. It maybe looks like it's right in between. But because we're estimating where the points are, that's another downfall to the graphing method. But definitely negative 4, 3 is reasonable. So instead of guessing where those two lines cross, sometimes, I'm not saying all the time, but sometimes you're going to need to resort to algebraic methods to know exactly where those lines cross. Okay, so when there is, in this case, where there is one solution, there's only one, we have a term, a phrase, it's 2 words. This is the solution in numeric form, so x is negative 4, y is 3. But we have a phrase that we use. We say that it's consistent, meaning there is a solution, and then it's not only consistent, but it's independent. Consistent, independent, meaning yes, there is a solution and there's only one. We're going to look at some examples where there is more than one solution. So both of these would be considered, obviously, consistent, independent. And just check the instructions. Sometimes you have to identify them. Independent. If it doesn't say to identify them as consistent, independent, consistent, dependent, or inconsistent, then you don't have to worry about this. But I just want to cover what those words mean as we work our way through these examples. Okay, so you've seen a graphing method. Graph the two lines, see if they cross. If they do, that point of intersection represents the solution. Here is the substitution method. We got the same answer, one answer. And now let's do this same system using a process called elimination. Elimination says pick one of these variables to, we could use the word cancel. And we do that by adding like terms. Think combining like terms. So if I left it as it is, and I just combined like terms, then the x's, these two would become 3x, this would become 9y, and this would become 15. Well, none of the variables cancel. And that's the goal of elimination, is to make one of the variables cancel. Well, in this case, it's going to require that I multiply one of the equations by something. I'm just going to pick a variable to eliminate, and then I'm going to have to multiply by a number to make that happen. Okay, so you could do x or y. I'm going to eliminate x, and I'm going to do that by changing negative 3x into negative 6x, so that when these are added together, they would cancel out. So to make that happen, I'm going to have to multiply the top equation by 2. Just remember, a common mistake I see in these problems is people get so focused on the variable that they're trying to cancel that they forget everything in that equation needs to be multiplied, in this case by 2. Now, I'm not doing anything to the bottom equation. You don't always have to multiply by both. Okay, so I'm going to eliminate, or we could think cancel, the x's with addition. Because negative 6 plus 6 is 0, 16 plus 1 is 17y, and 72, that's really like minus 21, is 51. So I got y is 3. And at this point, there's no difference between elimination or substitution. You just pick one of the equations, it doesn't matter which, pick the one that you think might be the easiest to work with, and replace, in this case, we're going to replace y with our 3 value, and then we're going to use that to help us solve for x. And as you can see, we got the same answer. So 3 different methods, and all 3 yielded the exact same answer. Okay, so that's an example of the 3 methods that we're going to be practicing in throughout this lesson. Okay, well, here's another graphing example. So I think I'm going to apply graphing by intercepts again. So if I graph by intercepts, the x-intercept, hopefully you can see, I'll do this top equation in red. The x-intercept is going to be 6. You just replace y with 0 and solve. 3x equals 18, so x equals 6. And the y-intercept, if I replaced x with 0, would be 2. Okay, so I just need those 2 points. X is 6, y is 2. And just grab my straight edge. For you, it'll be a straight edge. For me, it's just going to be trying to line these 2 points up and get a running start. And there is the graph of the top equation. So the bottom equation, if you wanted to do the same thing, you could. Just let, if you wanted the x-intercept, let y be 0. So that means negative x equals negative 6. So x is positive 6. All right, same x-intercept. If we wanted to solve for the y-intercept, let x be 0. Negative 3y equals negative 6, so y is 2. Wow, that's the same line. Okay, and you may have noticed that right off the top. The top line, the top equation, is really dividing by 3 across all the terms, and that will give us the bottom equation. Or if you go the other way, it's the bottom equation multiplied by negative 3, sorry. Dividing by negative 3 gives you the bottom. Multiplying by negative 3 would give you the top. So this is an example of the way we'd interpret this is that every ordered pair that exists on this line, okay, and it doesn't matter if we know what they are or not, that's not the point, but just think about how many ordered pairs are on this line. Well, there's an infinite number. This line goes forever and ever in both directions, negative infinity to positive infinity. So when this happens, when it's the same equation, as it turns out, it's really the same line presented in 2 different equation forms, but when we simplify, we see that it's really just the same equation. Then we're going to say that there's an infinite number of solutions, and I'm okay if you just abbreviate as INS, infinite number of solutions. All the ordered pairs that we could find on this line represent solutions. And then just like where there's one answer, we said we call that consistent and dependent. When there's many answers, more than we could ever count, we'll say that that's consistent and dependent. It's easy to remember. Independent means one. Dependent means many. And again, you only have to do that when it's asked for, but I'm just going to go ahead and cover what those mean. When you see those in instructions, I want you to understand what they're talking about. All right. Let's take a look at what that looks like if you were to encounter it with substitution. All right, so I'm going to just run through the substitution process. I'm going to solve for x on the bottom. You could solve for any of these four, but I think you should pick one that either has, in this case, I don't have a 1 coefficient, but -1 is almost as good. So to solve for x, my first move would be to add 3y. And I don't have solve for x here, but just think either divide or multiply by -1. And now it's solve for x. And so now I take this and I put it in for x in the top. So solve for a variable in one of the equations and then replace that variable in the other equation. So this is what infinite number of solutions looks like when you're using an algebraic method. Well, first of all, you'll notice that the variables cancel. 9y minus 9y is 0. And the constants that remain are, they make a true statement. 18 is equal to 18. So this will always happen when you have the infinite number of solutions. It's probably easy to see on the graph because we know there's an infinite number of ordered pairs, but in this case, I'm not looking at the graph, so I'm just kind of giving you a heads up. When this happens, where you just have a true statement after the variables cancel, this is another way of showing infinite number of solutions. And then again, that's called consistent dependent. Okay, elimination, I'll just go ahead and run through this with you. This is what will happen, same system, but if we use the elimination method, we're trying to make one of these variables cancel. Well, in the process of making one of them cancel, they're both going to cancel. So I'm going to multiply the bottom equation by 3. First of all, I'm going to turn this around. I just like for it to be in order, x, then y. If you didn't turn it around, it would be okay. So 3 times -x is -3x, 3 times -3y is -9y, and this is -18. And so we're going to eliminate with addition. Well, both variables cancel. 18 plus -18 is 0. Well, that's true. So the same situation will happen, except that both of your variables, when you're trying to eliminate one, you'll actually eliminate both. And if the statement that remains is true, this is another way of saying infinite number of solutions for consistent dependent. So I just showed you the same result using all three methods. Okay, let's take a look at elimination. This is a little bit weird, so I just want to give you a heads up. We need to first arrange our terms. And if you're given variables other than x and y, just think alphabetically. U comes before v, so this would be like the x, and this would be like the y. So I'm first going to arrange my terms so that they match up. So in elimination, you should have variables on one side and then the constant on the other, and just put them in alphabetical order. Here I'm going to add 6u to both sides. And now I'm going to pick a variable to eliminate. Really doesn't matter which. If you wanted to eliminate u, I'll just do it both ways. If you wanted to eliminate u, then you could do 6 on the top, -11 on the bottom to set up elimination by addition. Because that would become 66, and this would become -66. I mean, obviously you could have also made this negative and this positive, and you would have had the same result. Okay, well let's say, well, what if you didn't want to eliminate u, you wanted to eliminate v? Well, then you could have taken this bottom 8 and multiplied by the top, and take this top 5 and multiply by the bottom, and now you're going to have -40v on the top, and you'll have positive 40V on the bottom. So now you've set up elimination again with addition, but that would enable you to eliminate V. Okay, so I'm just going to leave it like this, and let's see what we get when we multiply by 8. 88U minus 40V, and then we have to do 35 times 8, and that's 280. Now we're going to multiply by 5 on the bottom, so this is going to be 30U plus 40V, and 62 times 5 is 310. So we've set the V's up to cancel with addition. Just going to put a plus sign there to remind me. So we add all the like terms. So 88 plus 30 is 118U. The V's cancel, and 280 plus 310 is 590. And so now we just have to divide by 118, and we got our value for U is 5. Okay, well now we go back to either one of these, it doesn't matter which. You could even use these two that we set up, U and V, really doesn't matter. Replace U with 5 and then solve for V. So I'm just going to go, again, you could use any of them. I'm just going to go with the top. And if I let U be 5, that gives me 55 equals 5Z plus 35. Subtract 35 from both sides. 20 is 5V, so V is 4. Okay, so when you're dealing with variables other than X and Y and you're writing ordered pairs, again, just think alphabetically. U comes before V, so in my ordered pair, 5 comes before 4. Okay, here's another example of solving algebraically, but this time let's take a look at a no solution. I'm going to use elimination here. I'm going to multiply by 2 on the bottom, and I'm not going to do anything to the top. So 2x minus 12y is 3. So across the bottom, I'm going to get negative 2x plus 12y is negative 18. Well, this time the variables cancel, both x and y, so I get 0 on the left, and on the right I get negative 15. Well, 0 does not equal negative 15. So if you're doing an algebraic method and this happens, both variables cancel, this is going to be the no solution. And when we have no solution, we had two other phrases for one solution, many solutions. If there's no solution, we say that it's inconsistent. And just to show you a graphing example, this would be if you were graphing two lines that were parallel. Okay, just a rough sketch here. Let's just say these represented the two equations in your system. This would be an example of inconsistent. The two lines are never going to cross. So this is, we would say this is no solution, and then we would follow that up with inconsistent. Okay, just wanted to set these up for you, and hopefully you can take it from there. So we're going to come up with two equations, just like we did, but these two equations come from this particular real-life scenario that we're dealing with. So we have a $10 coupon that Jerry Lynn can use, and she's also got the choice of a 15% discount coupon. All right, so what I'm going to do is I'm going to let a variable represent the amount of what she purchased. Maybe that's clothing, the dollar amount of what she purchases. And then I'm going to let Y be what she actually pays, because she's going to get a discount off of these. So this would be like on the ticket. You know, you're shopping. Maybe we could say the price ticket. How much that would be if we add up all the tickets of the items. And then Y is actually going to be what she paid. because there's going to be a difference. She gets a discount off of this ticket price. Okay, so the $10 coupon would be like this. We would say she's going to pay the amount of the ticket price, but she's going to get $10 off of that. So there's one equation to represent using the coupon. Okay, for the 15%, I'll say $10 off. $10 coupon. Well, here's the 15% coupon. She's going to pay that original amount of the ticket, but she's going to get, so for the 15%, it's like she's going to pay the original price, whatever's on the ticket, but then at the register, she's going to get to deduct 15% of whatever that ticket price or the sum of the tickets were. So we could bring this down to 0.85x because those are like terms. Okay, so here's the deal. I've got it set up for you. So think substitution. Substitution says solve for a variable. All right, well, these are both solved for y. So it really doesn't matter which way you go. You could let 0.85x equal y in this equation. So what we have here is a system of two equations. And we're supposed to solve this. Okay, so when I let 0.85x replace y in this other equation, I'm using substitution. Now I want you to go ahead and solve for x. Okay, I'm going to leave it from here on. I want you to go ahead and find out what x is. But I'm going to tell you what x represents. Since we let these two equal each other, what that means is it really doesn't matter how much, it doesn't matter which coupon we use for that amount of purchase. Okay, so what we're finding here, in business we would call it kind of the break-even point. So at that value for x, it really doesn't matter whether you use the $10 off or the 15% off. Well, then I want you to pick a number that's either above or below that and plug that number in for x and let that help you decide, okay, when would it be better to use the coupon 15% off or the $10 off. Okay, so I'm not going to give too much away. I want you to find that number, and I'll just throw something after. Let's just say that it's $100. It isn't, but let's just say it is. Well, what that means is if you're spending $100 on purchases, it doesn't matter whether you use the $10 off or the 15% off. So what I'm going to do is, well, what if it's 101? Does that give me an indication? So you're going to plug 101 back in for these x's and see if that gives you a hint as to when would it be better to use, when would you save more when it goes over 100 in this case. Okay, would it be better to use the $10 off or the 15% off? Okay, so I think we set that one up pretty well for you. And now let's set another one up. Okay, so Levi has, he's got a job, but he's got another job offer, and he wants to know, he's a car salesman, so he wants to know, the question is how many cars must he sell per month, or how much should he sell in price, not the number of cars, but the price of those cars, to make which job would be better for him, and which job would he make the most money is the bottom line question. So I'm going to let X be the answer to the question, the amount of money, amount of sales per month. Okay, so the offer, there's going to be two equations in this system. We'll call the top one the offer, and then what he's doing currently. So this would be the new job that he's thinking about taking, and we're going to compare it to his current job. So Y is the number of sales per month, and then or X is the number of sales per month, and we're going to let Y be how much money he makes per month, because he's got commission, he's got a flat rate that he's going to be receiving. I'll just call salary, total salary per month. So for the job offer, his total salary that he's going to receive, he's going to get $800 a month, period. Whether he sells one car or 100 cars, they're going to give him $800 a month just for being an employee. The rest of his pay is really going to depend on how much he sells. So this equation is going to be 0.02x. He gets 2% of the amount that he sells. And then he gets this 800, which is just going to be given regardless. All right, that's the offer. What he's doing currently, he gets $1,200 a month, whether he sells 1 or 100. And then the rest is based on how much he sells. So we get 1.5 as a decimal, 1.5% times how much he sells. He's going to get that amount in salary, plus the rest of his salary is going to be $1,200 flat fee. So this is kind of like the other problem. I want you to let these two equations equal each other. This is just using substitution. And I'm not going to go too far. I want to see what you come up with. So when you let these two equal each other, at that number for X, let's just say, this is not right, but let's just say X is $1,000. That means he sells $1,000 worth of cars per month. Well, for $1,000 a month that he sells, it really doesn't matter. He's going to make the same salary. Okay, so what I want you to do is tell me, okay, based on this number, would it be more than this? Would it be less than this? Kind of let that be your guide and see if that number can give you a hint as to which would be better for him to take, depending on how much he sells each month. Okay, so let this be your starting point, solve for X, and then go from there and tell me based on that number. If he went over that number, then the job offer would be better, or I'm going to let you decide what the final answer should be. Okay, so I think I've set those up pretty well for you. I've given you the assignment. If you have any questions at all, feel free to reach out, and I'll see you next time.